All right, good afternoon, class. So this is section 6.3b. This is our very final lecture for this class for chapter 6, and you can feel good about yourself. You've made it this far. Uh, so this is the last one where I'm going to have new material from after this point. This is just going to be a review and preparing for the final exam. So for today, 6.3b, we have one more case of the integral we want to talk about. So far, we've all been dealing with the indefinite integral, which is when we're trying to find the antiderivative and we have that plus c on the end. Plus c, well, I'll think about it later. At any rate, so far all we've done is the indefinite integral. We've used our basic integration rules, and then we use those rules in tangent with the u substitution rule. So we have all of the tools we need in order to integrate something, but now we want to talk about what is called the definite integral. So this is 6.3b, and this is the definite integral. And to put it in simple English, the point of the definite integral is to, I'm going to put this in quotes because we'll have some formulas and definitions later. The point is to find the area under the curve. And what do I mean by that? Why do we care about trying to find the area under the curve? Well, if you think about it, if we have a simple function that's a flat horizontal line, and maybe I'm looking at this function from A to B, then all I have here is a rectangle. And to find the area under the curve, which is the area between this line and the x-axis, all I got to do is length times width, and I've got the area. So why would I need integrals? Well, suppose instead of a simple shape like this, suppose I had a function that was instead something like this. And you wanted to get the area from A to B. And now you got this strange region that you're trying to find the area for. It's got this strange curve on the top. It's not really a half circle because, well, this curve isn't a half circle. There's just a curve at the top. So it's not a half circle. So using a circle formula for area is not going to help us here. Well, in fact, we don't have any equation that will give us the area for such a shape. This is where the definite integral comes into play. So if I want to find the area under this curve from A to B, then I have to use what is called the definite integral, which we write as the integral from A to B. So I label the bounds top to bottom. So A is less than B. It's assumed from left to right that when we're looking at the x-axis, that A is some number to the left of B. So A has to be smaller than B. So we're integrating from A to B of f of x dx. And so there you go. This is the formal symbolic notation for how to write the definite integral. But how do we solve this? How do we go about such a problem? Well, first, let me just go ahead and make notes here that A, as we've discussed, is the lower limit, and B is the upper limit, which makes sense. A is lower, B is higher. So there you go. But how do we do this? So this is the area under the curve. This is area. Why is that true? Well, first, let's take a look at how this is actually solved. When you're trying to solve such an integral, then we already know how to integrate this. The antiderivative of f of x we've been using so far as big F, right? So the integral of f of x dx is equal to some big F. right? And then plus c on the end. Well, when you're trying to find the area, then what we end up doing is we take big F of b. Since b is the upper limit, it's the upper approximation for the area, f of b, and we'll subtract the lower approximation, big F of a. And so we end up with no c's left over. It's just big F, the antiderivative of b, minus the antiderivative of a. Why does this work? Where'd c go? Why don't we have c anymore? Well, if you think about it, if we're saying that it's f of b minus f of a, then okay, how would this work out? So this integral would be, we would have some big F, we would have some big F of x, and other notation would be we want to evaluate it from a to b. So once we've found our antiderivative, I write this bar to the right of it to indicate I want to find this antiderivative from a to b. Then we're saying this would be big F, and we're saying there should be a plus c there, right? So there would be big F of b plus c, and then we'd have minus f of b minus c. But then we got a positive c and a minus c. The c's cancel, and we're left with big F of b, and my marker is dying on me right in the last lecture, minus, that should be an a, big F of a. So we don't have any c's here. And our answer is just going to be the antiderivative with b and a plugged in, subtracting against each other. But if you're still not sold on it, let me use a simple example that we can all agree on. Suppose I have the function, and I've got a horizontal line. This is y equals 2. And I want to find the area from a equals 2 up till b equals 5. So before I even do any integrals, we already know how to find the area for this. It's 2 units tall, and 5 minus 2, it's 3 units wide. The area of this is 3 times 2. Our answer should be 6. But now, if I do the integral of this constant function, 2 dx, and I'm doing this from 2 to 5, then what do I get? Well, the integral of 2, the antiderivative of 2, is 2x. I want to evaluate it from 2 to 5, and so 5 times 2 is 10, minus 2 times 2 is 4, 10 minus 4 is 6. So we do indeed get the same answer regardless of which way we try to solve this. And admittedly, yes, this integral is probably a lot more work than it's worth when you're trying to find the area of a rectangle. But suppose that instead you have like some weird wibbly wobbly thing and you want to find the area between those two areas. So that's this area and this area, and you got some area under the x-axis there. Then suddenly it's not so simple as just use the rectangle formula. In this case, using the integral is going to be our best bet. So there's a simple example that hopefully proves to you that this does indeed work, and it does indeed solve for the area. Another way to think about it is when you're integrating the line 2 and you get the antiderivative 2x, then this adds like an extra slider. We've got this x slider, and depending on what bounds I'm looking at, that tells me how far apart on this 2 line am I looking at. Well, I'm looking at it from 2 to 5. And now that I've got this x here, I can multiply and subtract the difference, and I can find the area by using this kind of slider idea. If that didn't make sense, I apologize. Don't worry about it too much. The long and short of it is just that when you're trying to find the area under a curve, you integrate from a to b for your f of x. When you find your antiderivative, you're going to have your bounds, your lower bound, your upper bound. you'll plug in your upper bound and then subtract what you get when you plug in your lower bound. And that's it. That'll give you your area every time. That's the formula you're going to use here. So some other basic rules that you can use when you're trying to solve the definite integral. You can see here actually that, so there's a few good things we should point out. And actually one of these is the participation activity for today, so pay attention to this bit. If you have an integral from a to a of some function f of x, regardless of what f of x is, it could be anything. It could be some nasty equation. But because I'm integrating from a to a, which is its same self, if you think about it on the graph, that would be like trying to integrate for some sliver of a line that has no width, right? And what's the area of something with no width? Well, it can't have any width. So that's an area of 0. So anytime you see an integral that's from some number to the same number, then regardless of what's here, you already know the answer is 0, and then you can keep working ahead. Don't even worry about what f of x is. So there you go. That's one thing, one nice trick. Another thing to keep in mind is when you're trying to integrate, and you've got the integral from a to b, and you got some constant times an f of x, well, just like indefinite integrals, constants can always be pulled out to the outside. So you've got k times the integral from a to b of f of x dx. And there you have it. So a lot of these same rules you've already learned, they're still going to apply here. The only difference is now we're solving for the definite integral, and we're trying to find the area under the curve between these bounds of a and b. And then lastly, as you might have guessed, if you have a function plus or minus another function, then you can always separate them on that plus minus. And so it's the integral from a to b of f of x plus or minus the integral from a to b of that g of x. So you can always separate using the same old rules we learned for indefinite integrals. Yeah, so that covers the basic properties, which again are just the same old properties that we've already learned with indefinite integrals. And now we'd like to cover one other thing you can solve using this stuff. So we have this idea for the area. It's this integral from a to b of f of x. But suppose you want to find instead what is called the average value. Average value. What do we do here? Well, if you think about it, what is an average? An average is when you take the sum of something and then you divide it by the number of numbers, right? If I have 1, 2, 4, 4, 6, and I want to find an average, then I would add up all of those numbers to get some number, and I would divide it by 1, 2, 3, 4, 5. And that would be my average. Well, if I want to find the average area, or in other words, if I want to find the average f of x, the average height of a function over this interval, then I'll just take the area and divide it by the amount of numbers I covered. But how many numbers did I cover? Well, I specifically covered the interval from a to b. In other words, b minus a. And so what does this actually work out to be? You just end up with a fraction on the outside of our integral times a, which is the integral from a to b of f of x dx. So this is your formula for solving average value. You are going to need that equation later, as you'll see in some examples. So there you have it. We have the indefinite integral, we have the average value, and now we're ready to move forward with some examples. Oh, and just one other little tidbit. I'd said earlier how we're assuming we're assuming that A is less than B for this bound from A to B. But suppose you're given a question where they flip it and they have B to A instead, but maybe A is still a smaller number. Well, with the rule with these integrals, we can only integrate from some small number to the bigger number. And when you flip it like this, it creates some problems. So what you can do to fix this is equal to the integral where we have a negative sign, but then you flip the bounds. And now we have it back the way we like with the smaller number being on the bottom, only you have a negative. So this might not be something that actually comes up during Hawk's learning, but it is something to be aware of in case you see any examples where they have the smaller number up top. So be mindful of that, and if you ever need to flip the bounds, you can do that, but when you flip them, just throw a negative to the outside and you're golden. Alright, so there you go. With that, we are ready to try some examples. So let's give it a go. Alright, so first example. Suppose I ask you, we're trying to integrate from 2 to 5 of the function 3x squared plus 2x plus 1, right? So this first step, all you do is just take the integral the way you normally would and find the antiderivative. So here we just have to use power rule. We're going to have x cubed divided by 3, but times 3, the 3's will cancel, plus x squared divided by 2, but again it's times 2, so the 2's will cancel, plus x, and that's our antiderivative. Normally we would have a plus c, but because we're taking the definite integral and we have these bounds, the c's will actually cancel out. So we don't have any c, and we're evaluating from 2 to 5. And now all we do is plug in the top number, find our answer, and then subtract what we get when we plug in the bottom number. So when I plug in 5, I'm going to have 5 cubed, which is 125, plus 5 squared, which is 25, plus 5, and this is my big F of b, to go along with the formula we had over here, big F of b minus big F of a. So now we want to subtract what we get when we plug in 2. And you want to be very careful of this negative here. I have this subtraction, but then I put this parenthesis here for when I'm plugging in 2, it's minus whatever I get with the function. So you want to make sure you distribute the negative when you plug in your 2. So just leave the 2 on the outside for now, but be mindful of it and be careful with it. Sometimes students forget about it or they don't distribute it correctly, and it'll throw off your answer. So be careful of that. Alright, so we plug in 2, and we've got 2 cubed, which is 8, plus 2 squared, which is 4, and then plus 2. So 8 plus 4 is 12, plus 2 is 14. So we've got minus 14, and this is big F of A. And then over here, when you add these numbers together, I'll just go ahead and tell you, you get 155. So our final answer is going to be 155 minus 14, or in other words, 141. And that's it. That's your final answer. And anytime you're solving these definite integrals, your answers are going to be these numerical values. Why? Because this is an area. It's some amount of space that's being taken up by this curve, and between the curve and the x-axis over this bound. And so you're going to have some numerical number representing whatever that area is. So there you have it. So let's take a look at some more complicated examples. Some other cases that start to throw together everything we've learned so far, and maybe you'll have to use some use substitution. So here we go. Suppose we have the question, what is the integral from 2 to 6 of 3x divided by x squared minus 3 dx? Well, based on this function here on the inside, there's nothing we can really do to simplify this. I can't break this fraction down. So my only other option would be to use some kind of use substitution. So how do I do this? Well, as we learned from 6.2, it's often good to pick the denominator. It's also often good to pick whatever has the highest power. In this case, we have an x squared in the denominator. So by all means, it looks like picking u as x squared minus 3 will be a good option. So in this case, we're going to have du is equal to 2x dx. But right now, we actually have a 3. So let's see, I want to get a 3 down here so I can plug it in. So if I want to get a 3, that means I want to get rid of the 2. So if I divide by 2, but then I also multiply by 3, then 2 divided by 2 will be 1 times 3. I'll be left with a 3x here. But whatever I do to one side of the equal sign, I have to do it to the other. So I'll have a 3 halves du over here. And so now I have 3 halves du is equal to 3x dx. And now I'm home free. Here's my 3x dx. And I've got this guy, he's u in the denominator. And now when I substitute the 3x dx, that's going to become du. But I've got a 3 halves on the outside. Don't forget the coefficient. And then I'll have 1 divided by u. And that's not so bad. That's going to be 3 halves natural log of u, but u is x squared minus 3. And now I want to evaluate from 2 to 6. So far so good. We had to use substitution to get to our antiderivative, but now that I'm at my antiderivative, I want to plug in my upper and lower limits. So when I plug in my upper limit, I'm going to have 6 squared. 6 squared is 36, minus 3 is 33. So I'm going to have 3 halves natural log of 33. And then when I plug in 2, I'm going to have 2 squared. 2 squared is 4. 4 minus 3 is 1. But recall from our natural log section that the natural log of 1 is 0. So I have minus 0 on the end, and I can just forget about it. So this right here is our final answer, and that's a perfectly good, valid answer right there. So 3 halves times the natural log of 33, even though that doesn't really look like a regular number, well, you could try to approximate it as a decimal. If you plug it into a calculator, you're going to get something like 5.24. So either of those are good answers. This one is a little more accurate because it includes all the decimal points, whereas this one is just a rounded answer. So, and depending on the question in Hawk's Learning, sometimes it might ask you to round 2 decimal places, in which case you want to go ahead and plug it into the calculator. Other times, it might ask you for the actual solution, the actual answer, in which case you want to leave it in this format because this actually has more accuracy. So take it or leave it. Either of these are good answers. This one's a little more accurate, but again, depending on the question, you might need the decimal format. So just keep that in mind. All right, so what else have we got? What are some other questions you might see in 6.3b? So let's see. What would be a good example? Okay, yeah, negative bounds. So suppose you have an integral from -5 to -3 of 5x squared. Now, don't be thrown off by these negative signs here. All that means is, for this function that we're trying to find the area of, we're looking at this space from -5 to -3, and that's the spot we want to calculate for. Oops, -3. So that's perfectly fine. You will run into questions that have that, so don't be put off by that. You do want to take note, though, that in negative numbers, when you have a bigger number like this, -5 is actually smaller than -3. So even though 5 looks bigger, it'll be on the bottom of the integral, which is where it should be. So don't freak out by that. That's perfectly normal. Don't move it anywhere. That's where it should be. Otherwise, you just solve this integral the same way you normally would. So we're just going to go ahead and use the power rule. So I'm going to increase the power by 1. I'll have x cubed divided by 3, but I still got my times 5. And I want to evaluate from -5 to -3. So I plug in my upper limit, and -3 cubed is going to be -27. And -27 times 5, I have written over here, is -135 divided by 3. So that's our upper limit. Now I want to subtract the lower limit. So I'm going to plug in -5. -5 cubed, that's 125. Well, that's a -125. But a -125 times 5 is still going to be a negative number. So when I have a minus negative, double negative, make this positive. So I have 125 times 5, which is going to give me 625 divided by 3. And so now all we do is just add the two together, and 625 minus 135 is going to give you 490 divided by 3. And that is a good, perfectly fine answer. Again, depending on Hawk's Learning, it might ask you to round this to 2 decimal places. Just put that into a calculator or whatever, and that'll give you your final answer. And there you have it. So you can do these definite integrals even with negative bounds. So don't let that throw you off. Just be careful of those negative signs, and be careful of these cases where you might have double negatives. You want to make sure you flip the sign and make it positive, because that will throw off your answer. All right, so what else have we got? So we've talked about what average value is, but we haven't had any example questions yet. So let's consider the case where they give you f of x is equal to 8x to the 6 plus 6 on the interval 1 to 4. And they want to know the average value. Well, using the average value formula, average value is 1 divided by 4 minus 1 times the integral from 1 to 4 of our function 8x to the 6 plus 6 dx. And now all we do is just plug and chug, solve the integral the same way we always would, except now we'll plug in bounds once we have our antiderivative. So here we go. 4 minus 1, that'll give us a third on the outside. We're integrating from 1 to 4, and then we still got 8x to the 6 plus 6 dx on the inside. So we're going to increase the power by 1. Oh wait, I copied something down wrong. Yeah. My mistake. Oh, that would have been awful. Sorry about that. It's not 8x to the 6th power. It's 8x to the 3rd power. That will change your answer quite a bit, and it'll give you a lot more work if you leave the 6 there. Yeah, so again, this is 8x to the 3rd power plus 6. And yeah, the rest of this is fine. Okay, great. So we haven't messed up too much yet. So we keep going here, and I'm going to have 1/3 on the outside. X will be raised to the 4th power. 8 divided by 4 is 2 plus 6x. I won't have any plus c here, and I'm evaluating from 1 to 4. So I'm going to go ahead and multiply my 1/3 to the inside so I won't have to worry about it later. And I'm going to have x to the 4th divided by 3 plus 2x. And now I'm ready to just plug in 4 and 1. So when I plug in 4, 4 to the 4th, let's see. 4 times 4 is 16, times 4 is 64, times 4 again. Let's see, 64 times 4, 256. So we're going to have 256 divided by 3 plus 8. And then we're going to have minus what we get when we plug in 1. So when we plug in 1, we're going to have 1/3 plus 2. And you work through this. On the left side, this is going to simplify to 5. Now hold on now, something does not quite look right here. Let me get my calculator and double check because something's not adding up. Okay, I'm back. So yeah, there was a slight mistake here. When I distributed my 1/3, I forgot about this constant 2. I should have left it here, so it was 2x to the 4th divided by 3. And so when I plugged in 4, I should have had 512 divided by 3. But the rest of this I think is still fine. Yeah, and this should be a 2 here. Okay, the rest is fixed now. It's saved. So we have 536 divided by 3 for the upper limit, and for the lower limit, we're going to have minus 8/3 when you add those together. This is going to give us a final answer of when you subtract these two fractions and you clean it up and divide by 3, it actually comes out quite nicely to 176. So there you go. There's your final answer. And there you have it. So that covers the basic examples for 6.3b. There are a few other examples that we could talk about, but it's all the same kind of stuff we've already solved. So I believe that gives you guys everything you need to be able to solve this. So for today's lecture, I'm actually going to end it a little bit early. Well, quite a bit early, but that's okay. Of course, if you felt like any of this I went over too quickly or something didn't make sense, by all means talk to me, ask me, send me an email. We can talk about it. We also have our Q&A will be in later in the day, and of course we can talk about any concerns you might have then. Otherwise, that's all I've got for you in this last lecture, and that's all of the material I have for you guys to learn during this class. So I hope you got something out of it. I hope it made sense over the course of this class, and I wish you guys the best of luck as you move forward in your collegiate careers. All right.